So hi and welcome. In this episode we're going to just quickly go over some of the software and tools that I'll be using throughout the course of this project, and I'm just going to quickly show them so it's not the first time that you're seeing it when we actually dive into start working with them individually here and there. And it would be too scattered to just pick them up as we need them and go along. So I'll show them and list them off quickly so you can get familiar with them if you want, find out which ones you're already familiar with, whatever. But I'll also release separate videos in the installation of each one, and those will probably be quick and easy and short. So I'll rapid fire those out just intermittently as I'm working on more complex or deeper videos. So with that, I'm going to start with Linux. As you can see, I'm using Linux here. As opposed to Windows or Mac OS, Linux is just an open source operating system. And I guess since we're going from the ground up, I'll start with the fundamentals. Open source just means that it's free to use, copy, distribute, use commercially or anything like that. You can even check the code and change the code if you want, recompile the entire operating system to customize it to whatever needs you have. That's why there's so many versions of Linux. I'm using Ubuntu. Specifically, I'm using a distribution called Mint. If you want to know more about Linux, I did a podcast with Jordan Roy, my co-host, on Frivolous Gravitas is the name of it. You can find it on iTunes. I think we're still up there. We've been on hiatus, and iTunes sometimes takes RSS feeds down when you've been on hiatus too long. But if you want to find the link to... Actually, I'll just show you. If you want to find the link to the RSS feed to grab it into any of your podcasters or whatever, you can just check out my website, chrisdriver.com. And there's a copy link way up at the corner here. So you just click it and it copies to the clipboard. And then as you can see, if I Control V, it's got the link to the RSS feed there. And that's how you subscribe to it. I'm going to be updating this with my research on this channel here under this research thing. But as you can see, I've done a couple podcast episodes on neural networks already with Jordan on that podcast there. So check it out if you're interested. But otherwise, you can find the podcast if you don't generally listen to them and you don't have a podcaster, or you don't know what an RSS feed is or whatever, that's okay too. Just do a quick search for it in YouTube here, and it should pop up as the first, Frivolous Gravitas right here. And videos, which one is it? That'll be, I think it's called Linux. Yeah, there it goes. Linux. So as you can see, actually, since I'm already on here, I've got some technical guides that are completely separate from the podcast, but we just threw them up on the channel anyway because I didn't have this channel going yet. So I'm going to re-upload these anyway under this channel because these are some introduction to coding, like programming, basic scripting, which I'm going to be covering a lot, so there's no point in me re-recording the same thing. But there's also like guides to like dual booting if you've got Windows but you want to follow along and use Linux because it's a much better operating system for this type of work. You can find a guide on dual booting operating systems here. You can find... what else I got? Concurrency and programming, and again, this is all in JavaScript, so it's very low, or it's high level, but that just means that it's easy to get started on it because it's not a complex programming language where you need a whole bunch of like grassroots fundamental knowledge to get started. You just open up a browser and you can start typing away. So I've got other live coding sessions on functions. This is probably the most important one, but I'll be uploading this soon on this channel anyway, as I said. And primitive recursion is really important too, mostly just to practice manipulating functions and stuff. But yeah, check out our podcast if you're interested. I got a whole bunch of other goodies in here. But yeah, Frivolous Gravitas. That's the name of the podcast. And that's how you'll find out more about Linux, because I've got a big 2-hour show about explaining what Linux is and how it works and all that kind of jazz. So, other than Linux, I'm going to start talking about some of the more subtle tools. I use OpenShot, which is just for my video editing, for uploading to YouTube and things like that. But as I start rendering sequences of graphics and stuff, I will very likely be using OpenShot also to publish animations. The graphics I render, I'm going to be doing those in Blender. This is going to be key to like all of the work that we do on this channel, because my intention is to throw in oops, that's shading. Where's scripting? There it is. The idea is essentially I'm going to write code in Blender here, because Blender natively interprets Python. It's got its own library called BPy. And as you can see, it's just a standard script. It doesn't do anything, but it's just sort of for demonstration purposes and just to set me up to, because I don't use it very often, but I'll get used to it soon enough, I'm sure, as we'll be using it. This here, opening the console, allows you to interact with the stage here. And then if you'll see, if I move this around, oh, down here actually. This is the console output, so if you have errors and stuff, it'll tell you what the error is down here. But as you can see here, it tells you the exact operation that's processed from within the Python interpreter, just for that movement I did with the cube. And anytime you move something here, it updates. So if you don't actually need to memorize the code for anything that you do in Blender, you basically just have to know how to do it. And then once you move it on stage, if you're watching down here in the info menu, the context menu, you can see exactly what code was processed to do the action that you just did with the mouse and visually and stuff. So that's really handy, because you can do things like, you know, scale vertically. And it tells you BPY, which is this import here, the ops, which is an object inside of BPy, and then transform is just a submethod of ops, resize is a submethod of transform, and then it takes in some parameters, and the value equals is a parameter that accepts the changes that you want to make. And how does it know what type of changes you're going to make? It's going to be a resize transform from ops from BPy. And then there's orientation and all this other kind of jazz too. So this is going to be primarily what I want to do with our machine learning algorithms, is plug it and process it through the Python interpreter inside of Blender, and then have it graphically sort of display here in an open stage, so that we can find a new way of getting visualizing our data, like the outputs and inputs and the constraints and the hyperplanes and the barriers and parameters and manifolds and topologies and all this kind of stuff that you're going to be dealing with machine learning programs. You're going to be writing it oftentimes in Python anyway. I'm going to start with I'm going to start by writing it in JavaScript though, because they both have a TensorFlow library, so they'll be almost identical and similar that way. But starting out programming in JavaScript will be easier for me, because I can teach the programming visually at the same time, because the browser's got graphical stuff integrated with it, as I've been showing you in other videos with Google Canvas. So being able to apply something to the canvas and understanding and practicing code and functions and stuff like that, then we can easily transition into like machine learning in a browser. And then because we're using the same, and then we'll plug that into a framework after we've done it like all manually from the ground up. And then once we plug it into TensorFlow to speed things up and to simplify the process that we did manually, then I can take TensorFlow and we can run TensorFlow in Python here, because the library is almost identical between both programming language. But as you can see, the syntax is just slightly different. But I'll introduce you to Python a little bit later, and we'll stick to JavaScript for now, just because I want to get the fundamentals and the grassroots down anyway, and I want to build a couple visual tools to help like before we get the data visualization through Blender in 3 dimensions plus time dimension plus 3 dimensions of color plus an alpha transparency dimension, etc., etc. Before we get into all the complicated stuff, I want to progress into it using JavaScript like we've been doing, and I'm going to make a couple tools to make that easier, and I'll make those tools work in a browser first. That way we can look at things like gradient descent and managing transformations of matrices and using imported modules and things like that gets kind of complicated if you're not already used to code. So going to be starting that way. But anyway, this is Blender, and as you can see, it's just a 3D modeling. So it's got lighting effects, ray tracing, and all that good stuff. You can even check out wireframes if you want. And add a mesh. So yeah, it's neat, it's fun, but as you can see, it calculates normals and intersects and stuff like that on its own, and that's a lot of the math that we're going to be doing with neural networks anyway. So I'm hoping that the optimizations built into this render engine to show 3-dimensional models and to build like a stage and sort of well, even like particle systems and fluid dynamics and stuff like that. Don't mind the dog. That can all be simulated inside of Blender too, which is going to be really handy because those optimizations from all the updates and upgrades to Blender are going to easily transfer over, well, hopefully easily transfer over to our machine learning algorithms. So that's Blender. You'll hear me talk about that a lot because that's going to be the prime focus of ultimately the end of my project here. As you've seen, we're going to use VS Code a lot, but we've been doing this for a while now, so you'll be familiar with VS Code already. Sublime Text, which I love, is just a simple text editor, whatever. But it's easier than loading up. VS Code's pretty resource heavy or whatever, and sometimes you need 2 text editors open, but VS Code is a bit chunky just to look at a text document or something. So it's kind of like my alternative to Notepad if you use Windows. I was a big Notepad fan back in the day, did all my coding by hand in Notepad. Chromium, obviously, I'm going to be using a lot. Chromium is just Google's open source type of browser. I'm not sure if it's technically open source, but I know that you can rebuild it to your own. Like Edge, I think, Microsoft's Edge is built on Chromium because Internet Explorer was so bad for so long they just couldn't bother to learn how to fix it. Other than that, what else I got? GIMP, which is, you've probably already seen this already too, but the image editor. So I'll just quickly show you. This is how I do all my graphics and everything, but it's not just for the presentation of the channel and things like that. I'm actually going to use it as well to make texture maps, and texture maps I'm going to be using as versions of how do I say it? It's like a visual representation of a matrix, right? So if you've got a matrix of numbers, you can interpolate them to 0 to 255 and get color values for all the RGB channels, the red, green, and blue. That's the color spectrum that works on, well, it's the standard color spectrum just for computer graphics, generally speaking, but it's not the only one. If you do high-end graphics and you need extra detail, there's better bit depth to like CMYK, and it's more accurate from screen to print if you use a different type of color space. But color spaces I'm going to be manipulating a lot in Blender, because Blender also has, like I said, the graphics render engine, and color and ray tracing means like tracing light paths and things through objects, which require like tangents and normals of the objects. And there's like a dampening effect or a fall off from light. Like the further you go from light, the dimmer it appears. That type of stuff is all kind of baked into Blender, as well as formulae and functions like Fresnel, sine, cosine, and all that kind of stuff too. So that'll be really handy. Understanding how you can manipulate color space is very, very similar to being able to understand how to manipulate weight space or vector spaces in general in in matrix multiplication, dot products, cross products, and all that. They're very similar to like ray casting shadows and things off of objects. So basically what I'm going to try and do with the models that I'm building through Blender is repurpose the things that are built to, like, say, cast a shadow, repurpose that for a type of algorithm that I'm building for machine learning subnet. And that subnet is going to be managed and controlled by a higher master net. I haven't really figured out what I'm going to call it yet, but Jan LeCun called it something like a consciousness thingy. I'm just going to check quickly because that paper was really interesting and I wanted to reference it anyway. Latest paper. Jan LeCun. I wonder if I can find an image quickly while I'm on here. Maybe not. Anyway, he's got his most recent idea is basically to have like a control center for his neural network that manages sub-networks. So let's say you had like a vision recognition system and a text recognition system. You could put those two together and get like shapes from text and be able to differentiate from the higher level. Hey, what am I looking at in this image that I'm throwing in as an input? And what you might get from an output from that would be this is either text or it's not text. That's a very simple neural network to process. But based on whether it's text or not text, you can have that neural network decide which direction to throw the output towards, to throw it into the pre-trained text recognition, and then it'll spit out a meaning, let's say, or a translation to those words or something. Whatever it's trained to do, it'll do it. But you can have a higher order neural network that manages the inputs of other neural networks. And that's sort of how I want to go about it using Blender, with those spaces and intersections and collision detection and all those built-in features. Use those to figure out how to or where to throw its output, following like its master control center or whatever. The theory is it's similar to how the brain works, where our brains are pattern recognizing systems too. That's why we call them these machine learning programs or algorithms, neural networks. It's because they're intended to sort of simulate the way neurons work. It's not a perfect analogy because neurons fire based on like chemicals and hormones and enzymes, and there are so many more factors that are infinitely more deep than, well, maybe not infinitely, but finitely many more deep layers to it than a binary computer system simulating a neural network can do. But with interpolation and normalization and a whole bunch of like statistical analyses, there are ways to simulate that type of gradient and variability within a neural network. So we'll be getting into that a lot too. One of the biggest things we'll be going into for Python though is Anaconda. And Anaconda is basically for statistical analysis and data sciences and things like that. I'll just quickly show you that. That's not how you normally start it. I write aliases for things that are easier for me to type and remember, which is one of the nice things about Linux too. Don't show me. Jupyter Lab, launch. So this is Anaconda, and it just gives you some options for like a space or an environment to set up. See, I've got one for Blender and one's just my basic one. And you can see I've got a bunch of scripts in here, and it just launches itself in a browser and launches on a server. So you can run Python code in blocks, and it's just much easier to deal with like segments of code instead of trying to do everything in a terminal and a text pad. You can see the outputs built right into the engine here, which is the benefit to using something like Anaconda when you're doing data sciences, because you can incrementally, step by step, sort of figure out like which part of your code is and isn't working. But so this is all Python, and this is an example of a neural network. So I guess if you want to see something train, I could just quickly run the entire system. So just Shift Enter, Shift Enter, Shift Enter, Shift Enter. My computer might start chugging here because I'm actively building and training a model right now. I'm not even sure if it works because I can't remember the last time I was writing this code, but assuming it works, I should be able to, oh yeah, it's running first epoch, no error yet. Yeah, so it's working. And the outcome is going to give me some set of scores, and then it's going to print those scores for me in a string format that tells me exactly in percentage terms how accurate it is. But this might take too long, so I'm just going to cancel it. Stop. Yeah. I'm told you should always log out or shut down of this. I'm not sure why, but I do it just because I don't want my code screwing up, because like if the logic is fine, but it throws an error because I exited wrong, I might start spend hours messing with my code when I don't have to, thinking that there's something wrong with the script I wrote when there really isn't. But one of the other neat things actually that came out just recently is Python now works in browsers too, so I'm probably going to transition from JavaScript in the browser and our tools and things like that to Python in the browser using PyScript. I haven't actually tried it yet, but I was meaning to all week and I just never got around to it. But yeah, Python apparently now works in HTML, so I just got to look into it and I'll do a video on that too. Yeah, I'm not going to do that now. So that's Python, Anaconda, Blender, VS Code, OpenShot. OpenShot uses other open source libraries, and I don't want to dig into every dependency of every piece of software that we use, just because there are hundreds of thousands of them and there's not enough time to go through. So I'm just going to go through the main composite ones that have, all the other little stuff built into them. And hopefully, if you're interested in finding out who produced all this nice, rich, good stuff for everyone to use for free, feel free to investigate and throw them a thank you or something, or a donation if you can afford it, because that really helps support the developers if you're able to. Other than that, for recording screen captures and things like that, I've got OpenShot running. That's pretty straightforward. Tor is awesome for security. I did a podcast on OPSEC, operational security, as well. Not really relevant to what we're doing here, but considering the tumultuous times of our era in censorship and mass surveillance and, government tyranny, widely speaking, in the information age, Tor is extremely important to the safety and security of not just, dissidents and terrorists, but journalists and individuals who are censored in their home countries, or who need to speak privately to their family members abroad or something like that. So I really want to just support, quick shout out to Tor and the Tor project, because they're pivotal in helping the human race progress as well. Other than that, I do my audio production and editing in Audacity. Audacity is another open source, and I think all of these work in Windows too. They have Windows versions. I know for sure Blender does, for sure Audacity does, for sure LMMS, the Linux Multimedia Studio, might not, but it might. GIMP definitely does, the image editor that we use. Stands for GNU Image Manipulation Program, but GIMP for short. I'm almost positive Sublime Text works in Windows, if you're using Windows. VS Code is Microsoft, so that definitely works in Windows. It was released by Microsoft. It's free. I'm not sure. I don't think it's open source, but it's free. And it's very, very good. I hate on Microsoft a lot, but when they do something right, credit where it's due. So good on them for keeping that free and open source, or not open source, but free for now. Freely distributed, and what I'm trying to say is it's accessible on Linux, which they didn't have to do, but they kind of did, because they're losing market share pretty quick. As you can see, Linux is a very speedy, quick, free alternative that's fully customizable and all that jazz. and it's excellent for writing code and programming, and especially great for web developers if you're doing web development, because most web servers are written in, or are structured in Unix-like systems, either OpenBSD or Linux itself. So like Apache Server is a free server, open source server project that's built on Linux, for one example. So if you're doing anything on the web, you don't have to use Linux, obviously, but it's nice to not have to like switch your brain bilingually between two different systems, like using backslashes for file paths in Windows and then using forward slashes in Linux. Like the reason why website addresses use forward slashes is because it's the Unix-based system. So it's easier to stick to one, and it's cheaper to stick to one, and Linux is more effective and quicker and more stable, and it's free, and you can customize everything right down to the toolbar. As you can see, my little start menu, you can change whatever written in here. You can change where all your panels are, how many start menus you have, all that kind of stuff. So that's, I got OBS, Audacity, Linux, OpenShot. I'm probably going to use Unity. Well, I was going to use Unity, which is a game engine. So once I had all my models trained and running, I was going to have them exported from Blender, the 3D models and everything, with like the color space and the stage space and all that, and then import them into Unity so that I could do more complex interactions with like particle systems and stuff from different stages and different assets. And the game engine itself comes with a whole bunch of like physics optimizations, which again, like physics-based rendering is one of the things I'm going to be applying our neural networks to, and to have those also work inside of an engine which also works on top of PBR would just be adding a layer of dimensionality to my progress, or my project here, which would be really nice. But recently Unity did something really stupid, and I can't remember off the top of my head, but it really pissed me off. Unity was in the news lately for something like with ads or tracking information or something like that. And they're laying off people. Yeah, so Unity's taken a real turn for the worse after I think they were bought out by somebody, or acquired by somebody, or merged with another company, or something like that. But the game engine used to be, but I'm kind of relieved because I didn't want to learn C#, which is another programming language that I've never used before, and Unity works with that. So I'm looking for alternative game engines right now. There are a bunch of options. Unreal is the most popular, so I might try that. There's like you're allowed like a free trial for research and educational purposes, but if you start doing anything commercially, they want payment, obviously. But I'm not going to be selling this project. I'm going to be giving it free to the world, so I'm pretty sure that means that I'll be able to use Unity engine instead, which is great because the new upgrades to it offer things like lumens, which is global illumination and light stage optimizations that are just like leaps and bounds better than anything else that we have on the market right now. But there's also nanite, which is a way of depth of field rendering only things that aren't obscured, so that you can have like orders of magnitude more geometry in a scene without your computer completely lagging and bogging down. So it's another efficiency that manages a lot of vectors, but it doesn't draw out or process the ones that are mostly static, like background mountains or something. So instead of having a rasterized image of mountains just like pan across as you move through space inside of a video game, you can actually have geometry of those mountains, and it can be obscenely detailed because the way the nanite works built into Unreal Engine is that it breaks down the geometry just based on what's in the field of view, what's nearest to you, and also the level of detail necessary to get like photorealistic quality out of it. But anyway, I gotta look more into game engines, but that'll be long after. It's gonna take me a while just to build up to get into Python and Blender, and then for me to run out of all the options I have in Blender is probably going to take an eternity too. So, but just some careful considerations. Like I said, it's stuff that we'll look into. So other than like JavaScript and Python, potentially C# if I have to in a game engine, but that'll be the last that we do. I might want to process. I've got an NVIDIA video card, so I might be using. What was I going to say? Brain fart. Oh yeah, I might be using Cuda programming, which is written in C or C++, something like that. They've got a framework that lets you communicate with your code directly to your GPU. And if I need to scale up my projects and I don't want to pay for like cloud compute just yet, I might try to use the Cuda. I don't know what they call it, a plugin or a framework or something like that. But it's basically an extension, and it's a very low level, it's just one step above assembly. Oh, okay, I should explain low level and high level. Low level code is things like a binary, ones and zeros that tell a program how to run. They're completely illegible, also known as machine code. That's like the native language of all computers and logic systems. One step above that is like assembly code, where you have like 3 or 4 character instructions. And those are things like jump codes, store in a register, read from a register, move to another register, like very, very simple, basic instruction sets. And those are as fast as, those programs are as fast as a human can possibly understand computer code at its most native level, but it's not technically native to the computer yet because it's still using numbers and letters. But it's as early as you can possibly get from our perspective. And then one step above assembly language is C. And the C language was extended to C++ to have a standard library of a bunch of useful applications, tools, and algorithms like sort and filter and things like that you're going to use all the time. And those are compiled languages. So they're less easy to just play around with, because every time you make a change, if you want to see it run, you have to compile the code, which means that it converts it right down to binary. But doing that means that it's super fast because the computer's reading it in its native language. It doesn't need to be like interpreted, right? So C and C++ are like ideal, but they're the hardest to write. Well, assembly is much harder and binary is impossible, but realistically speaking, in pragmatic terms, those are the hardest to, those are going to be the hardest to write. But I might need to do them just for, depending on the scale of the algorithms I'm trying to train. But that's the benefit to using a framework like TensorFlow that I mentioned before. PyTorch is another one, because I can write code in Python or JavaScript, and it's going to translate the code I write, compile it into C, and then the C library built in the background there is going to do all the heavy lifting for us. Plus, it's got all the optimizations. Like it'll write the algorithm better than I ever could, because it's written by like genius programmers who collaborated and worked together and improved upon it. I think Google, again, credit where it's due, Google released TensorFlow free of charge, so anybody can use it and practice and play around with neural networks on it. Not just neural networks, but machine learning in general. But that's how they run in the background. So the reason we're using Python is because it's nice and readable, it's accessible, and we can do all our data science on it. And the reason we can do data science on it so well is because it translates everything into C or C++, and it runs much, much faster than Python could natively. Plus, it's already got the most optimum way of implementing the algorithms packaged together in the bundle that we're going to be using. That bundle being things like TensorFlow, NumPy, Keras, PyTorch. You'll hear a whole bunch of different types of these things, and that's that import line that we were putting up at the top of our Python scripts. So first we're going to build them, just hack and slash them together in JavaScript, but then we're going to start using frameworks and libraries, things that are built by other people who are done much, much better for the purpose of practicing machine learning algorithms. And we're going to do that, or for training models, I should say. It's not for the algorithms. Like, you still got to do the algorithm yourself, but you can implement it in the framework or through the library to actually make it like able to run, because most computers would just crash if you try to do everything in JavaScript, because JavaScript relative to C is mad slow. But the JavaScript engine is surprisingly fast these days, given the popularity of JavaScript over the years and the development through Chrome, which was a huge success again for hobbyist programmers like myself, thanks to Google. Google developed a V8 engine to process JavaScript, which is both now compiled and interpreted. So it does that compilation check just like C and C++ does, but it does it really quick as the browser is loading, and then it interprets halfway as it goes along the way. And you can also write, I think as I showed you before, just with like a Control-Shift-I, pulls up your developer tools here. And if you check the console, you can literally just write in here x equals 3, and then, what was it? You can just type x is 3, or x plus 5, 8. See, it just spits out the responses. So that's like being interpreted, and this is how Python mostly works, is that it's an interpreted language where you tell it what to do and it does it, just basically translating on the fly line by line, whereas a compiled thing would go through all of your code, do all of its checks, and sort everything around and throw it into a really fast machine code in the background and then run that machine code for you after you've compiled or built it. So that's high level, low level, Python, PyScript. I'm really big into Cellular Automata, and I want to see if there's some way of applying that to our algorithms too. And through the work I'm doing, I think I'm probably going to stick with Wolfram programming language, Mathematica, things like that. But that'll probably be if I'm still not at the AGI level, even after I've done everything I wanted implementing my algorithms into Blender, and then having those render into frames, and then having that export objects and models and particle systems and physics systems into a game engine. After all that, if I still haven't figured this out, I'll probably have to I'll probably start working maybe on a separate paper, but an extension of this paper that goes into Cellular Automata, which I don't want to get too much into it now, actually. I'll do an episode just on Cellular Automata in the browser, but basically it's just when you have a whole bunch of discrete independent systems that are wrapped in a Markov blanket or their own space with boundaries. So like if you think about the cellular world, cells have their own sort of scale that they work at and operate at, and it doesn't really make sense to talk about cells from larger scales or from smaller scales than from the Markov blanket of the cellular structure. So as an example contrasting that, if you were going to talk about quantum mechanics, where gravity is like insignificant to particles that are that massless. I mean, they're not technically massless, but they're so little mass in a particle that gravitational effects are nothing compared to the strong and the weak nuclear force and electromagnetic force and that kind of thing. So based on the scale that you're operating at, you have a Markov blanket that basically describes what's relevant to that scale of space. And Cellular Automata, I'm not talking about like cells. It's just, they're called that because that's sort of how cells are envisioned to replicate. They have a very limited subsystem of instructions, and based on that, they either pursue food, multiply, die, or build up a defense system or sleep. Like those little things that it does are based on a very primitive instruction set like DNA, which only has A, C, T, and G as options, but it encodes all of life forms that we know of through those molecules and compounds of those molecules based on the physical structures and rearrangement of all those amino acids. So that would be like a Markov blanket would be around the DNA structure itself, because it's a molecular size, and then it has very little to do with the physical dynamics of cells. I mean, it affects cells because cells operate on the instruction set built into the DNA, but the DNA is on a different scale of relevance, so it has a different Markov blanket with respect to like the data science and statistical analysis that we'll be implementing and employing for neural network projects or any type of data sciences, really. It just doesn't really make sense to talk about quantum mechanics and cells at the same time. But that doesn't mean that they don't affect the other. It just means that we don't have a realistic or reasonable way of tying the two together. So one is essentially irrelevant to the other from within its scope and scale. And these types of terms, you'll notice I'm using, are based on programming terms, and it's sort of just the best way I can describe it, just probably based on my lack of expertise and knowledge. So hopefully I'll get better at explaining things as we go along, but doing demonstrations and showing how they relate to one another, I think will be really beneficial in getting a fundamental knowledge and understanding of how things are running under the hood in the background, and how the math actually applies to reality and physical spaces, because those extend and translate beyond just what we're doing in codes and scripts and graphics and all that good stuff. So other than that, that's basically all the software I'm going to be using. Well, I'll call it tools for now, because I'm going to come across some that'll be helpful later on. And then, of course, nothing ever stagnates in technology. Things are always improving. And if new tools come out, I'm definitely going to try playing around with some new tools. So other than that, programming languages, I'm going to skip C# probably because of the game engine thing and the issues I have with Unity these days. But Lisp is a huge one, because Lisp operates with recursion and basically functions with anything super well. It's a very low-level language, though, and I haven't learned it yet. But Wolfram language and Lisp are probably going to be the two last languages I get into after, if I find that I can't scale up my models well enough, and I can't afford cloud compute still at that time. If I still need a way to produce a proof of concept, I'm going to have to try it in one of those types of languages. But mostly what we'll be using is Anaconda, a web browser, Blender, a text editor for coding, graphics editor for making texture maps of the data that we get, so that I can convert things from numeric structures and matrices into something graphical that I can actually recognize and look at. Our eyes are very good at pattern recognition, so I'm hoping that making things more visual is going to make more intuitive sense of really complex math that's hard to grasp. And the reason we need to grasp it is because we're manipulating interactions of dynamical systems and subsystems of those dynamical systems across many dimensions. So that's, I mean, on a single layer, that's too much for a brain to wrap around without a whole bunch of like practice and development and, neuroplasticity helping you out over time. But to do all of those structures in constantly moving and interacting systems, I think is probably impossible without some type of visualizations. It's certainly impossible without optimizations, because the space, it grows exponentially with each layer, and exponential growth is intractable. That's the curse of dimensionality, as it's called in machine learning. And I'll probably do an episode on that too, because that's a really important concept to appreciate when trying to optimize models. It's not just about speed of training or running, it's that they're physically impossible to run or train because of this curse of dimensionality, being that spaces within spaces don't multiply, they grow exponentially, and then they multiply within all of those exponential dimensions of space. So the more parameters you have, it doesn't scale linearly, it actually scales exponentially, and that gets out of hand really fast when you have more than a true-false output that you're trying to establish. Things like general intelligence inherently and intrinsically require that type of broad-based set of parameters and outputs. So the reason why we haven't developed an AI that is generally intelligent yet is strictly speaking because of the curse of dimensionality and this problem that I'm describing. So we're going to get around that through optimizations, hopefully. And the optimizations, instead of writing them from scratch and understanding like computer science at a PhD level, I'm going to re-implement other optimizations that work in nature, things for like light bounces, refraction, reflection, ambient occlusion, black body radiation, you name it. We're basically going to try and repurpose every physical structure, every known physical structure of the universe, and I'm going to apply that as some sort of parameter within my master model for the controller, and then I'm going to use that to process inputs to all of these other trained models for things that we know we can train, like edge detection, face recognition, color, what do you call it? Color picking. We have an algorithm that can figure out what color is what on a space that might be like shaded or overly illuminated or something like that. You can well, we know that it's possible, and it's been done even on a home computer to train a model that can detect actual colors based on the amount of light that's being shone on that object that has color. So that's the type of stuff I think is important, probably enough for this video. And yeah, it was just quickly to show you all the tools that we'll be using, just so that you're familiar with them, and then not familiar with them in the sense that you know how to use them all per se, but at least so that when I do bring it up and mention it, it's not the first time you're hearing of it, because that's just going to make it harder to follow along. If I bring up like 3 tools at the same time, that's already a lot. But then if I start using all 3 of those tools at the same time and you've never heard of any of those 3, you're going to have to like stop and look each one up individually, and that could be like a day for each thing that you look up, right? So now you're a little bit more familiar with it when I mention it. When I say GIMP, you know I'm not talking about a crippled person. I'm talking about an image manipulation program. When I talk about Linux, you know I'm talking about my operating system here. At least you know it's not necessary that yours looks exactly the same way as mine, or that you use the same operating system as me. Just so that you know the stage is being set for our contemplative exercises moving forward. So hopefully that was helpful at all to some of you newbies. If you're not new to any of this, you're probably bored out of your tree, but that's okay. You definitely can skip.